Until space telescopes, only astronauts had seen the visible universe ablaze with stars with such clarity against the velvety blackness of space. But the very atmosphere that protects us from lethal radiations from the sun makes life difficult for astronomers, who must view the universe through an atmosphere that absorbs much of the light. That's why they come to Hawaii, not for the warm ocean, but for the cool, dry atmosphere at the summit of Mauna Kea, Hawaiian for White Mountain, the highest point in the Pacific. Here, above much of the lower polluted atmosphere, some of the world's finest telescopes are assembled to exploit one of the best seeing sights on Earth.
This telescope is built to a standard Cassegrain optical design, which consists of two mirrors, a large primary parabolic mirror and a much smaller hyperbolic secondary mirror. The radiation from a distant star comes down through the opening in the dome, strikes the primary mirror, goes back up to the secondary mirror, and then down to the Cassegrain focus through this hole down to the instrument package below. Here at the Cassegrain focus, we have a cluster of instruments which detect the signal and send it through to the control room. Now, of course, in order to observe these objects, we have to keep the telescope pointed onto them while the Earth rotates. As you can see, we have computers almost everywhere in a modern telescope operation. This screen is used to help us acquire objects and track them for periods of several minutes or even up to several hours. It also, from here, we can select which instruments are to be used on the back of the telescope. The typical images that are first obtained by an astronomer are obtained in this control room. We do not nowadays use the eyeball to see objects in the sky. We have them displayed in control rooms on displays like the ones we have here. Those images are then sent on to computers and made available to astronomers all over the world.
Such images are of great importance in advancing our understanding of the cosmos. But to extract the most information from them, astronomers require high spatial resolution to see the fine details.
At visible wavelengths, high spatial resolution, access to fine detail, is vital to many areas of astronomy. Studies of our sun, the planets, clusters of stars in our own galaxy, and observing fine detail in distant galaxies. In our sun, one of the major problems is understanding the transport of energy from the central regions outwards. And we need to study the surface movements in granules, and to do this we need a high degree of spatial resolution. In planets such as Jupiter, we can actually observe aurorae very much like those on Earth. Going further out into our own galaxy, we see rich clusters of stars, but we need to be able to focus on the individual components of those clusters, the individual stars, and high spatial resolution is needed to be able to access this detail. Beyond our own galaxy, we can look into other galaxies, into the spiral arms, look into star-forming regions and the nuclear regions where material appears to be rotating around a central black hole.
Modern computer-controlled telescopes like this use super-sensitive detectors to record high-resolution images of even faint objects at all wavelengths, right across the visible spectrum, and even beyond in the infrared.
Beyond the visible in the near-infrared, there are numerous areas of research in which high spatial resolution imaging is very important. One of these is planetary studies. We can resolve the heat radiation from individual volcanoes on the surface of Io, the satellite of Jupiter. In star formation studies, we can also resolve circumstellar disks around young stars. These stars are embedded deep within molecular and dust clouds and are obscured in the optical. The disks themselves may go on to form planetary systems at some later time.
So how do we achieve high resolution? Even with a perfectly shaped mirror, the atmosphere distorts and blurs the image. But there's a more fundamental limit to the resolution, the mirror diameter itself. For example, you can photograph the rings of Saturn with a 125mm mirror. But, ignoring the atmosphere, you can see a lot more detail with a 2500mm mirror. So, ignoring the atmosphere, all we have to do to get better resolution is build bigger mirrors. But that's not easy. For to get anywhere near the fundamental limit, the surface must be accurate to better than 1/10 of a millionth of a meter. Otherwise, the light waves will not form a sharp focus. Furthermore, the entire mirror must retain its exact shape as the telescope moves to track the object. How can this technological feat be done? One way has been pioneered by Roger Angell at the Stewart Observatory Mirror Laboratory in Tucson. A relatively thick but lightweight honeycomb structure that is so stiff it remains rigid as it moves. However, another approach is catching on, actually bending the mirror itself. This is the European Southern Observatory's new technology telescope at La Silla in Chile. Its 3.5-meter mirror is too thin to retain its shape as it moves, so it must be continuously bent to compensate the errors. It has active optics.
Active optics, actually, I think is a good name because active must be seen in contrast to the word passive. So the normal telescopes you see on the mountain and elsewhere are what I call passive telescopes in the sense that you set them up according to their specification on their supports for the optics and so on, and then they just stay there. Now they degrade with time because their areas creep in because of the movement of the telescope, and the telescope can't do anything about it. So if you want to put it back into shape, you've then got to offline go and readjust it, which is a laborious operation. Now, an active telescope has two fundamental advantages. First of all, that you can relax certain manufacturing tolerances, and that means you can correct it afterwards in situ. And then the next advantage is what I like to express as automatic optical maintenance. In other words, the telescope all the time looks at itself optically, analyzes its own quality, and corrects itself. So it automatically maintains itself optically, and that's what it's all about. It does it really by what is a very simple principle. You see, if you take a slab of glass like this mirror, which is a meniscus disc, and as it moves, it tends to bend because of this movement, and these bending forces bend it in certain so-called bending modes. In this case, it's 5 modes that you have to correct. And therefore, what you do is you have what we call an image analyzer, always on the telescope, working online. And this analyzes the image in terms of these modes. And then in the computer, you have stored information. Okay, you've found telescope that you've got these errors. Now you correct them with pre-stored information in the computer, and that brings it back to its virtually perfect quality. The most important active optics mode is nothing to do with the prime mirror, it's to do with the position of the secondary. In other words, the classical error of passive telescopes is centering, decentering error. And this leads to an error which we call coma, and this is the sickness of all normal telescopes. That's what limits their actual quality. But if you can activate the secondary, as we have here, and you can move it systematically, you can calculate how much you have to move it to always remove this error. So we can remove this error with incredible precision. And this normal error, which is the worst thing in any of the other telescopes, is effectively zero.
So active optics has helped make the NTT one of the best optical telescopes in the Southern Hemisphere. Back in Hawaii, the mighty Keck Observatory also uses active optics. Inside is the world's largest optical telescope, with a primary mirror 10 meters in diameter.
This primary mirror is unusual in that the primary is a mosaic of 36 hexagonal segments. Had we built the primary mirror out of a single piece of glass, it would have been prohibitively expensive and very risky. A mirror of this size, whether it's a monolithic mirror or a segmented mirror, would deform objectionable amounts due to the varying forces of gravity as the telescope tracks the star. To overcome this problem, we have built an active control system which continuously monitors and adjusts the positions of the mirror segments with respect to each other to keep the primary mirror in its proper shape while we're tracking a star. To explain this in more detail is better done by looking at the back of an individual segment. Here we are in the mirror segment storage area. This is where we store our 6 spare mirror segments. And from here is an excellent place to see the back of the mirror segments where the active control system components can be viewed. The active control system consists of 3 actuators that go here, and here, and here. And the perimeter of the mirror has 12 sensors located along the edge. Each of these sensors has a paddle which swings out, which mates with its complementary component on the neighboring segment. The signals then from those 168 sensors, which cover the entire primary mirror, are read, and that information is processed to produce 3 times 36, or 108 commands, which tell the actuators how to move to put the mirrors where we want them to be so they form the desired optical surface. Let's look at an example of how the active control system works. Here we see an image taken with the active control system off, where we've let a certain amount of time go by, and changes in time and temperature have caused the segment alignment to degrade. This next image shows the effect of turning the active control system back on again, and now you see the image is restored to a nice sharp image.
With a 10-meter Keck mirror, we might expect to see detail as fine as this. In fact, we only see this. No better than with a primary mirror just half a meter or less in diameter. So what's gone wrong? Imagine these are light waves from a distant star. After traveling for perhaps thousands of years without changing, they enter the Earth's moving atmosphere, which distorts them in the last 100,000th of a second of their journey, just before entering the astronomer's telescope. Twinkle, twinkle, little star is not what the astronomers want to see. Even in high and dry mountain sites like this, good seeing can become poor seeing. In fact, it is rarely possible to improve on the resolution obtainable with a modest half-meter mirror. So is there a way to remove these atmospheric limitations? One way is to use yet more flexible mirrors.
This is an example of a deformable mirror of the type we plan on using to compensate for atmospheric turbulence. This mirror has 19 actuators. The type we would use for a large astronomical telescope has several hundred, and we're building systems of that type. This is a prototype of the larger one. The mirror consists of a thin faceplate on the front side, which has been silvered to act as a mirror, and an array of electronic actuators, and you can see the electrical leads which are driven by a computer to give the correct signals. The idea here is to monitor what the atmosphere is doing to a point source, such as a star, diagnose those signals in a computer, and derive a set of drive signals for these electronic actuators, which will deform the surface of the mirror a very slight amount, only of the order of a few wavelengths of light, but enough to correct for the turbulence and restore the image which would have been present if the atmosphere were not there.
Let's see how adaptive optics works. The light waves, distorted by the atmosphere, are intercepted by a small mirror. The waves travel on towards the image detector. But before they get there, a partially reflecting mirror sends a part of each wave towards the image analyzer. The output from the analyzer is fed to a computer. It compares the actual degraded image of a bright guide star with what the image of the star would look like if there were no atmospheric distortion. The computer then sends a signal to the small mirror to deform it, to compensate for the atmospheric distortion. The atmospheric distortions change rapidly, so the mirror has to be able to respond equally rapidly. It can do so because it is small and lightweight. And in doing so, all objects in the field of view of the telescope become clear. And that means everything from point stars to huge extended dust and gas clouds.
The difficulty comes in that there are very few stars that are bright enough and which are close enough to objects of interest in order to use these natural guide stars, or beacons as they are called. What we try and do is to create our own natural guide star by shining a laser and reflecting off of sodium atoms in the upper atmosphere to create a pinpoint of light high in the atmosphere to serve as our own guide star, which we can position any place we want. And in fact, we can move that beacon to follow the Earth's rotation so that the whole field of view and the guide star move as a unit, allowing us to look for long periods of time at very dim objects.
Active optics is tough enough, but adaptive optics, to compensate for the blurring effects of the Earth's atmosphere, is quite a bit more difficult. Here at Keck, we plan to start with natural stars to correct for the Earth's atmosphere to improve infrared images. Later, we plan on introducing a laser beacon to create an artificial star, and that should allow us to sharpen the images all the way down into visible light, where we should have enormously sharp images of stars.
So even if a convenient guide star like this is not there in the field of view, astronomers now have the means to create one. Here's an early experiment with adaptive optics using a small segmented mirror looking at a sunspot. In this split-screen display, you can see a lot more detail on the corrected image on the left. What will adaptive optics mean in practical terms?
It's somewhat amazing that this telescope, which is quite large, does no better for high spatial resolution imaging than small backyard astronomers' telescopes. In fact, the only thing people have been able to do in the past to achieve high spatial resolution is to send telescopes to outer space. This is very expensive, of course, and very difficult to do. Now we're entering a new age where adaptive optics and laser guide stars will be able to deliver this high spatial resolution from the ground, which allows us to image large numbers of astronomical objects. In fact, this technology will be applicable to astronomical observers for the observation of anything from planets to stars, to clusters of stars, and on to galaxies, and even beyond.
Even as modern ground-based telescopes fitted with automatic optical correction reach their fundamental limits set by the physical size of their mirrors, astronomers are seeking ways to achieve even higher resolution. Like radio astronomers, they hope to combine the output of their telescopes optically in a feat called coherent interferometry.
With the two Keck 10-meter telescopes and in addition 4 smaller auxiliary telescopes, we will be able to do coherent interferometry. We'll bring the light together from all of these telescopes and interfere that light. With that system, we will have a telescope with an angular resolution equivalent to that of an 85-meter diameter telescope. With this exquisite resolution, we should be able to study fine details in things like the most distant galaxies in the universe.
On the top of this remote mountain in Chile's Atacama Desert, the European Southern Observatory is building 4 8-meter telescopes. Each mirror was cast in a single piece and is thin enough for active bending. When the light from all 4 telescopes is combined, it will be the most powerful optical telescope on Earth, with an effective mirror 133 meters in diameter. But wait, if now the resolution depends on the size of the array and not on the diameter of the individual primary mirrors, why bother with big mirrors at all?
Large apertures makes it feasible to observe faint objects in a reasonable amount of time. The ability to see faint objects means that we can observe deep into space, further out into space. And by being able to do that, we're able to observe a larger volume of space. And inside a larger volume of space, we are therefore able to observe a much wider range of phenomena.
So, with large mirrors joined together as interferometers, astronomers should one day get all the spatial resolution they want, even for faint objects. Who needs space telescopes now? Well, this building is totally dedicated to a space telescope operating high above the Earth's atmosphere at an altitude of 590 kilometers.
Named after Edwin Hubble, it's the most complex, ambitious, and costly telescope ever built. Let's go see some of its first scientific images. As the incredible images in these pictures show, there's an immediate advantage in being above the atmosphere. The big advantage of being in space is to look at wavelengths which are completely absorbed by the atmosphere. Gamma rays, X-rays, ultraviolet light. For the most energetic processes, like those occurring in the middle of this nearby galaxy, NGC 4261, you want to look in X-rays and in ultraviolet light to see what exactly is going on in the middle of this galaxy, possibly a massive black hole. There, too, space-based platforms are able to avoid the emissions of the atmosphere and have unique advantages. In between, large ground-based telescopes with adaptive optics can study nearby galaxies and distant galaxies, the structures of these galaxies, and faint stars to offer us all the in-between processes that get us from the beginning of the universe to where we are now. We need both. We need ground-based telescopes and we need space-based platforms to give us the whole view of the universe.